Yeah, so I'd like just to present you a little bit, Naser. So for those who don't know Naser, he has been collaborating with Ana Filipa for quite some time in biometrics. He works in the Fraunhofer Institute and also explore other topics in machine learning and also information fusion. And he agreed to give us this presentation on explainability in biometrics, and which is a field that many of us working. So yeah, I think this will be very interesting. So Nasser, the
Thank you
floor
very
is
much, Philippe. And thank you for the invitation, guys. This is always fun. As you said, we'll talk about biometric explainability in biometrics with a focus on this difference between classification and matching that we use in biometrics. As you said, I'm with the Fraunhofer IGD and TU Darmstadt. I can tell you shortly about the institutes. I'm sure some of you know about these institutes. Fraunhofer IGD is part of the Fraunhofer Society. It has over 70 institutes in Germany working on different topics. There is also, I think, 7 or 8 locations outside of Germany, including in Porto. And with over 30,000 employees, we work applied research, so something very similar to INESTEC. So we do research, but really close to the industry. I am also with TU Darmstadt, where I am professor of biometrics, human analysis, and behavior understanding, part of the computer science department. This university is very research-oriented, so something very similar to University of Porto. Just wanted to give you, promote the institute first, and then get into our topic, which is explainability. And when we talk about explainability, when we want to explain decisions made by machines. My presentation is created to be more interactive, so I kind of had to interact with myself now, as this is online, so forgive me for that. We want to make decisions first to explain them. So, for example, what do we see here in the picture? I think most of us will say we see a salad, but we want to know, why is it salad? Why did I or you guys decided that this is a salad? And the first explanation that comes to my mind, probably also to many of you, is that this has tomatoes, onions, and cucumbers. So I think it's a salad because it has the components of the salad, which is true. It's our human intuition when it comes to salad, because maybe when it comes to something else, it's different. When it comes to salad, we look at the components and we say that this is probably a salad because it has these components. But machines might not follow our same intuition, may not look into only the components or the components at all. Machines, if asked why is this a salad, might tell us it is the components. It has tomatoes and onions and so on. But it might say that, okay, the reflection of the components there indicates that there is certain chemicals that correspond to salad. It might simply say there is a glass bowl and wood spoons. And for the data that I learned from, this is usually a salad. It might even say that just the existence of glass and wood makes it a salad. With this, I just want to say that the decision explanation does not need to be our intuitive explanations. It can be something else, because the machine can make the decision in another way, not necessarily the way that we make it, not in the form. So it doesn't have to be the components or the location of certain components, as we will say later, and not in the content. Even if we're looking at, for example, the form of I'm looking at what the components, the contents of the image, it might be different contents, that would make a certain decision. Okay. the main point we want to talk about today is that most explainability work that we see in the last few years is about classification. So there is a network that classifies an image or a sound or any kind of a signal and explain its classification decision. However, for so many problems like biometrics, it is not a classification problem, as we'll say later. But let's start with how the classification decision is made, so we know how this is different in the other cases. So we ask, for example, a classifier, which salad is this? And to train a classifier to answer us this, we train a classifier that just classifies potato salad and chopska salad. This is a Balkan area salad that's good. And this classifier will train to make a decision. It's potato salad or chopska salad. And then we want to make this decision. We show an image, let's say a potato salad. It's an image we didn't see before, but it is one of these classes. And it will tell us, yes, it will tell us this falls into the class of potato salad. So when we want to explain, sorry, when we want to explain this decision, this explanation is only based on what's going on in this network, one feed-forward operation of this image within this network, okay? But when we have a different question, which is not what is this salad, when we want to ask, are these two salads, are the same salad, you know? It's something that is a relation. It's not just an explanation of, it's not only a decision classification. We are asking, are these the two same salads? Then we are explaining a relation, and we want to make a relative decision. Not only asking what salad is this, as we said, we want, are these two salads are the same salads, you know? Then we have this network that is trained for classification. We use it just usually to get an embedding, or we use another network to get an embeddings. And we compare by the embeddings of these two salads, just to see, compare between them and see how similar they are. And if they are above certain threshold of similarity, we say, yes, they are the same salad, or not, they are not the same salad. This operation includes two feed forwards in two networks, usually networks that are the same, but two feed forward operations. There is a comparison operation and there is a threshold operation. And therefore, we can see that explaining the decision at the end is much more complicated than just one feed forward. So, for example, typical classification explainability solutions like GradCam will not do anything here of a meaning. And all these contribute to why I say these are the same salads or not the same salad. And this becomes more complicated because, for example, here we have two different salads, caprese and Greek salad. So they are, for us, at least as a label, they are not the same salads. We need to know what makes them the same salad, why they are the same salad. And what makes them not the same salad. So what components, whatever is in these two images, makes these same salad, and what makes them not same salad when they are not the same, but also when they are the same kind of salad, what makes them similar and what makes them not similar, you know? Because there is these four cases in the relationship if we want to know if two images belong to the same class or not. So based on this, we know that explaining relation decisions between unknown classes depend on multiple feed-forwards operations, as we said, if we're comparing two or more things. And there is the comparison and thresholding operations that are also related to why a decision is made. There is also the need to explain what makes two data points similar and what makes them dissimilar, because they will contribute to two possible failures in the decision. For biometrics, for the recognition in biometrics, this is always the case. So it is always the case that we train, at least in the real use cases. We can do it differently, but this is the real thing that works well, is to train a classification network. And this classification network later is used just as a representation, as a presentation layer. So we just use it to get a template and embedding that represent the identity of a certain image or a signal. Later on, these two embeddings are compared, and this comparison result in a similarity score. The similarity score is thresholded to say, yes, they are the same people. Or so for biometrics, we always need this relation. We always have this relation. We need a decision based on the relation. Here we come to the point of what to explain and how to explain it. So for the salad, we went for the components intuitively, but what we do when we have faces. I will give a simple example here. For example, for each pair we see here, is the faces of the same or different people? If I ask you, as I am alone here in the room, I cannot ask you for real. I would say if I was you, I will find this one very easy to make a decision that they are not the same people. This one in the middle and the one to the right, I find it much harder to make a decision if it's the same person or not. This one, I don't know, because maybe they are very similar, but this one just because I don't see very well who's in the image, So for me, the most confident decision, it was on the left, and the least confident decision probably here to the right. Okay. We need to know that this way I did, I'm sure you did, that that this is easier and this is harder to make the decision. But for face recognition that you are using on your phone or in the airport, we don't have this. The face recognition does not give us an indication of confidence. Is it easier decision or harder decision? Okay, and this is something I find strange, at least. Okay. So to find an indication of how easy is that decision itself, if it's the same person or not, confidence, we need to look at the decision, but also at the comparison score. How similar are these two faces, and get an indication of how confident we are. Here we start by what to explain and how to explain it, and we want to find the certainty. This is how of comparison scores and subsequent decisions. So of what we get here as a comparison score and what we get here as a decision. There are in recent couple of years in more research direction towards finding solution in this, and I will give an example of something that we did, just to give an indication of what we will talk about. Score uncertainty is interpretation of propagated uncertainty of comparison scores. So we need to know what is the uncertainty of comparison scores and the reliability of the decision, so the decision confidence. Okay. What we did, and there is different ways to do that, is by looking at our confidence in the embedding itself, okay, and propagate it to the score, okay? So given a face image, face recognition model M, you know how to, that most of the models during training have a dropout. in previous work that we did and others, we know that we can know how confidence in the decision in the model is in making the embedding is related to the fact that introducing dropouts in the feed-forward process, different dropouts, will result in a very similar embedding. So let's say if the model is very decision that's making the the correct embedding for a certain image, introducing different dropouts will result in similar embeddings, you know? This related to the face image quality and also how good the model deals with this face image quality, you know? Sorry. And therefore, we can calculate uncertainty of the embedding in each feature dimension. And the cosine similarity, of course, is a function of two embeddings. And therefore, these two embeddings have these two uncertainty factors, and we can propagate the uncertainty to a score uncertainty. So here, by propagating the uncertainty, we get a score uncertainty. So how uncertain we are in the comparison score between two images. The decision then is a function of this score that we calculate uncertainty and the threshold. And we can further propagate uncertainty to get decision confidence. An example of that is, for example, these two images here. We can say that their comparison score is 0.42. It doesn't mean 42%, it's just a relative number, plus minus 0.1. And the decision is that they are the same person with 62% decision confidence. Now the question comes is that when we get a comparison score, like this comparison score, 0.42, and we know, for example, that the threshold that we make decision on is 0.3, let's say it's 0.3. The intuitive way of looking at the confidence is that, okay, if it's the similarity is much higher than 0.43, then I have a higher score certainty, lower score uncertainty, and therefore my decision is more confident. But this is not always the case. It's not a linear relationship between the score certainty and decision confidence from one side and how far away you are from the threshold. So, for example, if we took the score certainty to be our confidence indicator, of course, it's a linear relationship from the threshold. So whenever we move to the right and to the left of the threshold, the confidence is this distance, so it's linear. But with a proposed method that propagate the uncertainty, we see that this is not optimal. So for example, in a bigger area around the threshold, the confidence is at its lowest. So even if you are a little bit away from the threshold and not directly near it, we know that this face recognition model is not confident. And later when it moves, there is an area that, yes, it moves linearly when we are more far away from the threshold, the confidence more linearly, and at some point far away from the threshold, we get a confidence that is saturated. So even if we move more away from the decision threshold, we are still quite sure that the decision is correct. So does it really work? We ask ourselves if this really works, like, is it really different than how far away we are from the threshold? For that, we just try to look what would happen if we removed the comparisons that have the least confidence, you know? And we assume that if our confidence measure in our score, and therefore also later our decision, works, then when we remove the lowest confidence measures, we eliminate the most probable errors. So therefore, the error in the remaining data will go down and down while we remove. So for example, let's take this case where we look at certain error, false non-match rates, or these false match rate, false match rate are just false positive and false negative. And we compare the intuitive confidence, which is confidence score is how far away we are from the threshold, to the confidence that is the propagated uncertainty. So what we proposed. When we move far away, when we remove more samples with lowest confidence, the error goes down with the intuitive confidence, as we would expect it. And it goes down faster in all the cases, in most cases, when we consider this propagated uncertainty. And therefore, we can say that this propagated uncertainty provides different information than just the score and how far away it is from threshold, and is more correct. So now we established that, yes, we can drive confidence measure of the biometric decisions. This represents the reliability of the decision from the model perspective, but only of the decision itself. We just get a number. Is it confident? How confident we are in a decision? But we can also explain different things in the biometric, in this relation, building this relation decision. We can look at the image itself. So what parts of these face images, for example, make them the same identity or not the same identity? As we said, there are things that would make them more similar. There are things that would make them less similar. Or if you're looking at salads, what parts of these images make them same salad or not the same salad? And if you think about it, when we looked at the faces, I would look at the eyes, the mouth, when I ask what parts of this image. But when I looked at the salads, it's not the same. I don't look, there is no like key points that I would look at, I'm going back to looking at the components. And this gives us back the notion that explanations have different forms, whether for us or for the machines. And based off that, just a grain of thought, like you can think about it later. Maybe the problems that you are working on is related to this. That for faces, at least for aligned one, our intuitive spatial answer is more related to comparing these areas of the image. But when it comes to salad, it's different. We didn't compare areas of the image. And remember, while thinking about that in reality, the spatial aspect is to a big part lost in CNN. However, we go back to our, let's not go so philosophical. Let's go back to our example. We want to know which areas of this image make them the same identity and which areas make them not the same identity. Also, in the last 2 years, there was different trials to find a solution for that. We'll see later that many of them work, but still not as good as we wanted to work. But I'm talking about one possible solution that we worked on, which we see here 2 images. They go through the CNN. There is an embedding, and we compare this embedding. And these embeddings have components xn, yn, so 2 vectors with xn and yn components. And the final similarity score is based on the score, which is the cosine similarity between these components, and the decision threshold, of course. Okay. Therefore, we assume that each feature in different dimension, at least, so all xn's andyn's in each feature of the first phase and the second phase contributes similarly to the match decision. Okay. And we can see which of the components in each embedding does contribute to a decision above the threshold, and which one of the components contributes to a decision below the threshold. Okay. And based on this positive or negative argument that each component will make, the gradients are back propagated to obtain the similarity or dissimilarity gradient map. So we get for each of these images a gradient map that have the components that represent the components that contribute to a negative decision and the components that contribute to a positive decision. If we considered here, we have the consideration of each components in the embedding contributes similarly to this decision, which is a very weak assumption. However, we made it. Then based on these negative and positive components, we create a mean map for the negative components and positive components. Here, for example, we say that the red dots are what makes this face different than this face, and the green dots is what makes this face similar to this face, and vice versa. Okay, because we can see that in some examples, these maps look like something that might make sense for us. In some examples, not so much. We want to see if it really works, and therefore we created images that has patches that push the comparison to a certain decision. So these are two faces we compare. However, we include patches from another identity to push a decision that is wrong, that these are not the same person, you know. That's the same for matching pair and non-matching pair. So we add also to matching pairs patches that will make them matching pair, you know. And we see if the maps that we create and other methods create do indicates that these patches are the areas that contribute to a matching pair in this case. You know? These are examples of the pairs we created, you know, with different levels. We have the maps here for this level, with the highest level of contamination. And these are just different methods to explain where are the components that actually contribute to the match and non-match, okay? We can see in some cases that, yes, this area, for example, here, does reflect somewhere here that it is an area that will change this to a negative match. Areas that are not manipulated are more in green. Other methods show something similar, however, not always the same. But in general, nothing is so shockingly clear. Nothing that shows us these exact components or areas of the face are really the contributors for a negative or positive decision. So we had to say, okay, we cannot only say that this works. You can see in this example is working clearly, in this example not, especially that some of this explanation is lost in the back propagation. We need to see really statistically if it's work or not. And therefore we look at errors, for example, FMR at a certain threshold. If we replaced these blocks batches with the correct batches, the error should go down as soon as we replace more of them, the error should go down, okay? If we replace them randomly, it's this gray curve. So also if you fill these batches randomly, of course, you will have a more complete image and the error will go to the minimum possible error in that case. However, if you replace them with an indication of this area is more important for this kind of error, FMR or FNMR, because we have this negative and positive contributions, then the plot should go faster. And the plot for the curve for our method and other methods actually does go faster than random. This means even if these images here still does not look very intuitive for us, it actually indicates much better than random which areas contribute to negative and positive decisions in a certain comparison. This, of course, is the same for other face recognition methods and for different levels of replacements. Okay. So by now we know that we can derive explanation maps of what makes what areas of the face or any other comparison contribute to similarity, what contribute to dissimilarity of identity in our case between pairs of images. We said they don't look always very intuitive till now, but they actually work statistically. If you look actually, they actually work very well. We need to look at the last thing of what we can explain. Also, we are running out of time. And how can we explain it in the case of this explaining biometric relations, you know? Instead of just saying which areas of face image contributes to a similarity or dissimilarity, we can actually ask what frequency components of these, for example, two face images contributes to the same identity or not the same identity. By frequency components, we mean, for example, is the high-level details, high frequency, contributes more to similarity of these two faces, or is it the low-level details, the lower frequency components contribute more to the similarity or dissimilarity of these two images? For that, we did something very simple. We just remove certain frequency components. So we split the image into its frequency components in a lossless manner, and we see the effect of removing each of the frequency component, and we create a frequency heat plot. So we say, for example, for a certain comparison, a certain image, these are the frequency components that influence, that will show a high similarity. And these frequency components show high dissimilarity, or a little bit high similarity, but in a negative pair, so a pair of not the same identity, you know. And we can see here examples of that. We can see the example comparing these two images. The low frequency components have much more till this level, let's say, higher importance. We see it also in a more fine frequency bands. And we see the influence of these components is more towards the negative, so they are not the same identity. Okay, if we look at the same pair of images in a lower resolution, of course, we can intuitively say that probably the high frequency components will have less importance, you know, and it is the case. So only most of the importance goes to the lowest frequency bands. It's the same in another example, more when we look at low when we look at low frequency, low resolution images, lower frequency have more relative importance. Here, sorry, contributing toward lower distance. So it's more positive decisions toward having the same identity, and here higher distance. So it is more towards negative identity. However, we can see, for example, sometimes that there is a certain frequency component here that indicates that these two faces are the same identity. but it is very small with respect to the others. Also here, we can calculate statistically if these actually make sense or not. And this is again by inserting frequency bands in our comparison and see if we inserted the most important ones, the error should drop faster than if we inserted random frequency bands. And actually, it is the case that when you insert the frequency band that we indicate that they are more important, then it drops faster. There is special use cases that we can use these facts with. For example, in morphing attacks. So in morphing attacks, you have two identities. One of them, for example, have a criminal record and the other not. And this one with a criminal record that is, for example, forbidden from traveling, can make a passport with a face image that is a morphing attacks, that the face image that can be verified by humans and machines to be both identities, B1 and A2 here. And with the A2 name and alphanumeric information, then B1 can use this morphing attacks, this passport or identity document to travel, for example, or any other cases. This is actually an attack that happened in reality. And it's a big issue because it's, in so many cases, very realistic to find. Wanted to look if comparing two bona fide, so not attack images of the same identity, or comparing this attack with one of these identities, actually produce a different pattern of which frequencies are important, okay? And this yellow one here is a result of bona fide. This yellow here is a result of comparing an attack with a non-attack. And the green line is like the average pattern of bona fide comparison. So what usually the bona fide comparisons look like. And we find that generally there is a difference between both, even when we're looking at different ways to create these morphing attacks. So in the bona fide, usually these frequency components are the most important. However, in the morphing attacks, the importance is usually more spread over more frequency bands. Actually, just looking at that and comparing any comparison to what bona fide should look like, you can do an unsupervised morphing attack detection that works pretty okay. Like it's far from random, you know? It's maybe above 80%, if I remember correctly, correct detection of the attack, just by looking. Thus, the importance of the frequency component in this comparison follow what I expect from a bona fide comparison. Other special cases is, can we also look at bias? So in face recognition, we are dealing with humans. There is this demographic bias. So face recognition and other biometric components can work differently for different demographic groups, including ethnicities, gender, and other groups, okay? And we looked, does actually the frequency band important differs between different groups? And also we looked if this is more clear when the model is more biased and less biased and so on. Just an indication, because we're not talking really about bias. It's a long, we need a longer term if we want to talk about bias. We can look here at this is the frequency band importance in average one for different comparisons. And we can see that, for example, relatively the lower frequency bands is not as important as other demographic groups in lower bands, but it becomes more important in comparison to other demographic groups in higher frequencies. We know now we can find what frequency components in a pair of image contribute the most or least to similarity or dissimilarity, again, these two cases. And this can help us understand a lot, for example, morphing and bias and so on. Okay. I'm already over time, so we are at take-home messages. explaining a matching decision, this relation is fundamentally different than just the classification explainability, clearly because there is more components. There is 2 feed-forward operations, there is the comparison, there's the thresholding, okay? Very important, salad is good for you, and whoever tell you that potato salad is a real salad, just say no. But for real, next time when you're crossing an automatic border control in Porto here in Frankfurt, know that rejecting you from crossing the gate, the e-gate, because of low similarity is very far from optimal. There is a confidence in the decision that can help you go through the gate lawfully and can help the border guards stop the right people more accurately. There is something better than just the comparison score, you know? And also when you go to the border guard, because you go to the e-gate and you don't pass through, you go to the border guard, know that there is at least now a start of a technology that can show the border guard that maybe this area of your face is the reason for the decision. Maybe it's your glasses, beard, or something else, you know? And be careful if you're a criminal and using a morphed image on your passport. The border guards and the algorithm can know, just because in the comparison with your morphed image on the passport, different frequency components have different importance than what we expect as a pattern. This might be an indication that your image is morphed. With this, I hope I didn't take so much time than planned. And I thank my colleague, Marco Huber, and other colleagues that most of this work is based on. And if you have any questions, I am happy to answer.